We're going to say at a point, at a point x, does f of x tend to hold in? This doesn't make any sense. On a specific value or limit. Home in, is that right? Home in. I don't know. I don't know if this makes sense. I wrote this up last night. Basically, does it come close to a value? That's what we're saying. Now, where limits are exciting for us are things that when you divide by 0 and cancel things out. If you remember the first graph we did this year was one where it was like x cubed minus 9 over x minus 3, and then we had a hole in the graph. That would be something where we'd say, well, x can't be 3, but what we're going to say is because it's very, very close, at 2.9999999, there's a value, and at 3.0000001, there's a value, would be a limit would exist at that point, right? So there would actually have a y value, you could predict what the value would be, even though you can't actually physically have it. And this is how we're going to get away from that, get around that point, and no one's actually fought me on it, because I think you guys are still scared since the first week. But on every single question that we dealt with, instantaneous rate of change, we divided by 0, right? Every single one. Right? And no one said, yeah, that's bad, we're dividing by 0. Not one person complained, and that's fine. Okay, right? But every single question we've done this year, we've broken math rules. All right? Calculus gets around that is because they're saying with the limit, they're getting very, very close to the value without actually getting there. So we'll say, instead of using 0, they'll say 0.0000000000000000000000001. Okay, that's how they sort of get around it. So I'm going to say here for this, just keep on with the note, and then we'll get to algebra. The algebra is more fun. We're going to say a limit exists if and only if both left and right limits exist and are equal. Okay, so the example of that one would be that graph of x squared minus 9 over x minus 3. We'd say the limit exists because on either point of that, on either side of that circle, we had a value that was the same value. Something like 1 over x, there is not a limit at x equals 0 because of the asymptote. If you think of the 1 over x graph goes, it looks like this. So there is no value at 0, right? Because it's infinity, and it's infinity if you go from the right, and it's negative infinity if you go from the left. So if you were to say what's the limit at 0, we don't know, right? Because there's 2 values. All right. We're going to say many limits can be evaluated by inspection, which are the boring limits. We're going to say most of today's lessons on the more complicated ones. That said, despite the fact that they're boring, you should always try direct substitution first. If you can substitute something into an equation and it works, do it. It'll make your life a whole lot easier. I don't do it that much, but I know Mr. Lacey often did that last semester for you got 2 years ago when we took the course. It would be something that looked awful, and you sub in 1, and it would have a value. Like it looked like something you have to cancel and cross and all that stuff, and it would work. So try and do it. This is what I call a boring limit. Here's my first boring limit. Here we go. Example 1 of a boring limit. Limit as x approaches 2 of 3x squared minus x plus 4. Okay, what that arrow says, lim stands for limit. X approaches 2, it says as x is getting close to 2. So that means as x approaches 2. 3x squared minus x plus 4. Okay, so this is direct substitution. That is 4 times 3 is 12 minus 2 is 10, which is 14. That's the most boring limit I've ever seen in my life. Okay, we did this back in grade 11. Okay, I actually taught my grade 11 class this today. Right, back something about that's boring. Where we get to more exciting things is where you have to use algebra to fix it. Okay, so these are the exciting ones. Come on. We're going to say if direct substitution ends in 0 over 0 or infinity over infinity. This is called an indeterminate limit. I'm almost on my note, don't worry. We should. And I have 4 steps listed. Okay. Mr. Lacey is a wonderful teacher. He taught me calculus. He is one of my teaching idols, and I want to be like him as a teacher. But he put in a number 5, and number 5 was magic. And I don't like magic in math, so you shouldn't put it in there. Or he used intuition, not magic, he said intuition. Okay, which basically is magic. Which means look at the problem and figure out how to do it. That's not a real mathematical stuff to solve an equation. It's magic. Okay, so I'm going to leave that one out. Okay, but the other 4 are good. Number 1 is fact. No, it's true. And for those, the bigger advanced function, look at your notes. That was in there. Intuition. I thought, I didn't say anything about it. He's going to watch this video tonight. I don't care. Math isn't math. Oh, that's true. We're on a good talk today. Let me try back. I don't know how to get back in Mr. Lacy's good books. What intuition means basically is you've had enough experience with limits that you can solve these. It's sort of like when you do identities for the first time and you say, wow, those are awful. And then somebody who's like your math teacher, like I remember there's Michael here, but some of my 3s couldn't do their limits. And Michael walked over to the grade 11 limits in like half a second. Okay, now why is that? Is that magic, or is it because he's done enough math that he's experienced in the different processes with it? So someone, again, like me, I look at these and say they're so easy because I've done a lot of this, that's not good. So it isn't magic, it's more intuition, it's experience, that's what it is. So that's why tonight for homework you'll be given a lot of these to practice up. When I say tonight, I mean this weekend. Okay? So you got it the weekend. All right, here we go. So here's the things. Factor and simplify, I've done this a lot. Factoring is factor and cancel. Rationalizing, we'll talk about that, how to get rid of that. One-sided limits are you check the value from the left and from the right, see if they're the same. And change a variable, those are the difficult ones. And I think hopefully I'll get to those today so I don't have to leave them until Monday. Although Michael, you do an excellent job with those, I am sure. I'll do example 1 and then Michael will do example 2. Here we go. Example 1. Whoops, sorry, I actually have 2 example 1s for some reason on my notes. Example 2 says, evaluate lim x approaches 2, 4 minus x squared all over 2 minus x. Okay, so initially what we're going to do, Nate and everyone else, is I'm going to submit x equals 2, because if that happens, we're happy, right? If I submit x equals 2 and we get a value, we're happy. Let me tell you, that's never going to happen in this course, ever. Okay, because this is an advanced function, this is calculus, right? So, so Nate, I'm going to pick on you. 4 minus 2 squared is what? Good. 2 minus 2 is? Good. So what's 0 divided by 0? Let's start over. It's indeterminate limits. It's not going to work. Can someone be brave and tell me how we can deal with this then? Go ahead. The square sounds good to me, okay? So this terms, I'm going to say equals lim x approaches 2, 2 minus x, and 2 plus x. Now, before I continue here, I get asked this every year. Do I need to write lim down my page the whole way? The answer is yes. You can only get rid of it when you do the evaluation, when you actually sub it in. then you get rid of the limit statement. Okay? All right, thank you, Joe. Why am I happy? Okay. 2 minus x cancels out. Wonderful. Now, hopefully you guys can see why we did all this stuff in grade 11 without the limit part, okay? Because it's the same thing. So this turns into limit as x approaches 2 of 2 plus x. Now here's the funny thing. X actually couldn't equal 2, but we're going to get around it, just like we did over here. So what does this actually equal then? Actually equals 4.
So that's where the whole would be.
And that, exactly, very good. The whole would be at x equals 4, but on either side it would have the same, sorry, the whole would be at x equals 2, and the y would be equals, yeah. So there would be a whole at x equals 2, so if we were to graph this, no, that's something, x equals 2, because there's your x value. So if you take a look here, that's 2, and the y value is 4, right? Yeah.
Sorry, can you say what a limit is exactly?
A limit is just basically, it's the value of the y value of something as you approach an x value. That's what a limit is, okay? So, as I said, because we can't, as we said here, I can't sub in x equals 2, like, because x can equal 2. So, as you get close to 2, the y value comes very, very close to being 4. That's all we're saying for this. So the x value, yeah.
It's sort of like asymptote behavior. Like as x approaches 2, the y value will approach 4, but it won't actually reach 4.
Here we go, example 3. I want you guys to try this. Then Michael's going to take up the solution for you guys. Here we go. Give that one a try, please. Okay? I'm going to pause the video. Michael will take this up with you in a moment.